You're watching Tea Leaves Programming. I call this series Programming Like It's 1979. Haskell for Dilettantes. A dilettante is, of course, someone who knows a little about a lot. And that's the perfect description of my approach to Haskell and functional programming. So where were we? I was talking about Chapter 3. We talked about lambdas. They also give list comprehensions. I hate list comprehensions. I'm going to be sad if a list comprehension is the best way to do some of these exercises because I just don't like the syntax. And it's very concise. You know, I appreciate why it exists, but, you know, I just don't like it. They also talk about tail recursion and rewriting a function to be tail recursive for efficiency. To their credit, they basically say, don't worry about this. Don't do this until you need to, and you should always write the function in the way that you understand it the best, which I think is excellent advice for almost anyone. So there are two sections. Oh, and they also talk about typed holes, which is my favorite feature of Haskell and some other languages, where you can put a hole, put something that begins with an underscore in your code, and you will get back some details on what the expected type of the thing that should go in that hole is, and also what do you have in hand that might fit that hole. Implement the function map maybe. Ooh, that sounds interesting. That takes a function and a maybe value. If the value is nothing, it returns nothing. If it's a just, it updates the contained value using the function. So this is a special case of the functor of fmap, basically. And in fact, the cheaty way to do this would be that. Let's see if that even compiles. Yeah, so that'll work. Length just ABC. Well, let's prove it. Length just ABC. Yeah, but that's not what they asked us to do, so we're not going to do that. We will implement it the way they intend us to, which is going to be like so. We're just going to use pattern matching for this. That's all that's needed. Continuing my campaign of annoying people who like single letter variable names. All right, that should be it. And indeed it is. Exercise 5. Implement a function capitalize that takes in a string and capitalizes the first letter of each word in it. You should probably define a helper function, capitalize first, that capitalizes the first letter. Why would I need a helper function for that? These functions will help. And so we're allowed to use toUpper. That's great. Oh, because we're going to capitalize the first letter of each word, not just the first word. So a helper function might help. And in fact, if we have a helper function that capitalizes the first letter of a string, that's going to have type. Let's do it. Capitalize first is going to have the type string to string, which is the same as type A to B, which means we could use it with map. And so the right solution here, we'll do it right now. That. Not even going to put the string on there. We'll do it point free. I think that would work. But in order for that to work, we need to actually implement it. Right, so for capitalize first, what are we getting? All right, this is wrong. right? That's a string. We're going to do that, which is going to make the argument to map a list of strings. And this is a little bit weird. I think this is a little bit weird because we now have this list of strings that is being passed around, but you'll note there's nothing in any of the type signatures indicating that. We could use a binding to, make that explicit, but that's the place where I'm going to get lost. That's the mistake I'm going to make, is like, I'm going to forget that. And then do that. So the flow here is, this gets evaluated first, creates a list of strings. Map capitalized first does its thing. And then we put it back together into just a single string. And so over here, we can just do this. And then it's to upper X, like that. Now this is making the assumption that we're getting a word, but I think it's a good assumption. Let's see if we did it. Oh my God, it worked. I want to see that work. I want to see it like actually work. And yeah, I know I can trust the tests. What are the chances that the tests would be lying to me? But I like seeing the code run. Gotta load it. All right, that works. Great, we are we're not halfway done yet. We're on the way. Another version of a while loop. This time, the check function returns an either value, my favorite data type. Not really. A left value means stop, a right value means keep looping. I will die on this hill. It should not be left and right. It should be error and success. I'm sorry, that's how I feel about it. The call while right check X should call check X, and if the result is a left, return the code. This is the same as what we just did, except we're actually using this either type. Okay, in. And so the thing is that I want a pattern match here. And here's where I'm weak on Haskell syntax. What I want here, oh no, I could do it this way. Case result E of. Now that I have a case, now I should be able to pattern match. A right value means keep looping. So we don't actually need that value. No, we do need that value because we've got to keep. I'm going to find out that I'm getting the case syntax wrong somehow, but that's fine. We'll figure that out. No, maybe not. Let's see, stack run Haskell, set3a test. All right, it passes. One of the things that I really dislike, I mean, it's unfair, right? Haskell makes it entirely possible to work with values that you can't print unless you implement a show type class for them. Hungry Joe, this is one of the, we have a question from the viewers. This is one of the rare examples where left-right makes more sense than success-error, surely. Yes, and again, I'm on board, or I'm open. I am overstating the case. There actually are people who use ethers all the time and use left and right the same, in an abstract way. My contention, so first of all, there's a structural reason with either, and I don't want to get into it too much, but if we look at the type of either, info, right? Because of decisions in how Haskell implements type classes and higher kinded types, these are not equivalent, this left and the right. You can't use them equivalently. The right value is kind of almost inherently and implicitly privileged above the left value. And the reason for that is that because of partial application. Because it's very easy for me to, create something that passes around in either A, and then I can complete it by providing a B. You really can't do the other way around. You could flip them, but then it's a different data type. My contention is that most people use either for its error success semantics. And so really kind of what I'm saying is the language should be providing a first-class error success type, and people who want to use it in a more generic fashion are probably better equipped to do that than the other way around. People who are looking at a maximally abstract thing and are expected to bring it into a more specific context. Really, it'll never change. It's not a serious argument. I don't think anyone is going to change the data type of either, ever. But still, I have to say it every time because it annoys me. Remember the lecture participants example from lecture 2. I don't, but we can go back and read it. We used a value of type either string int to store some measurements that might be missing. Implement the function sumWrites, which sums all non-missing measurements in a list like this. Challenge, look up the type of the either function, implement sumWrites using the map and either functions instead of pattern matching on lists or either. Ooh, challenge accepted. It's like they knew I love pattern matching. Look up the type of the either function. I misheard them. I looked up the type of the either type. Either. It's an A to C or a B to C, and an either AB returns a C. So given some either that contains a value in its left or a value in its right, we're going to give it two functions that are both going to return the same thing. But I don't know how we can do that in a world where what we're trying to go for is an integer, right? Because I can't go from an A to an integer. I can go from an A to an integer. And the reason I can go from an A to an integer either A to C, B to C, and we're starting with our list of ethers, right? List of ethers. Map xform LOE. I had an epiphany here. I don't think I actually can map xform as is because it's not if we have, this is a function going from write, the value contained in write to int, which is just extracting that value. All right, I'm gonna come back to this one. I feel like I'm spinning my wheels, and this is one where I need to go away and think about it a little more. And it's the sort of thing where in the shower I'll probably realize, oh, I made this dumb mistake. One way that I sometimes deal with issues like this is I will ignore their challenge, use pattern matching, and then having solved it one way helps you see how you solve it the other way. But all right, so I got stuck on some rights while I was doing the live stream, and I got frustrated. I said, I'll do it later. And then I did it later by myself while recording and got to the right answer. But I'm still unhappy about that I kind of flailed my way through the syntax to the right answer. So this is a case where I understood what I needed to do. I even understood what I needed to do step by step. But because I approached it in this top-down and bottom-up way at the same time, I essentially blundered into syntax mistakes, which then were sticky. And I had to take the whole thing apart before I could get it back together again. And so I'm unhappy about how to explain how I arrived at the right conclusion. So I was literally asleep. I was thinking of it as I was laying in bed. And I came up with a way to decompose this one step at a time. That, I should be clear, was not how I reached the answer, but is how I wish I reached the answer, now knowing the answer. So I'm going to take a crack at doing that here. And I'm going to do it with a lot of comments and a lot of type annotations in those comments. Let's see how this works. And I'm hoping that those comments and type annotations don't screw up the syntax. So, some rights. And I'm going to flip back and forth between this and the shell a lot. So, we know almost certainly that our sum rights is going to involve summing a list, right? And what's the type of sum? It goes from sum t of a to sum a. So we know that our a can't be either a int. We pretty much know that the output type of this has to be int. So whatever we're looking for from our sum has to go from a list of int to a single int. And that's our call to sum. Okay? And we're going to think about this in terms of steps. I don't actually remember exactly how many steps there are, but we'll figure that out. So our either a, and let's go ahead and use this as an example. Right? That's what we're starting with. Where do we want to get to? Well, we want to get to a list of ints, which would be, in this case, 1, something, 2, right? So what should this something be? The hint that we were given, or the challenge we were given, was to implement sum rights using, quote, map and either. Well, map is a functorial operation. So what that means is that whatever solution we come up with, we're not going to change the structure of this list. We're only going to change the contents. So it is impossible, if we're using map and either and not, say, filter, we're not going to end up with that. we are going to end up with something in the middle. Well, logically, if we're summing these things, what we would like to end up with is that. All right, so we yeah. Which is going to be an int. Right. So, how do we get from this to this? Well, this is going to be the map, right? And that's a map, so that is from this type either a int to int. So right. Now the challenge here is we're also told to use this ethers function. And this is where import data ether. Right? This is not a function by itself that can be fed to map. Map wants to go from A to B, and this is, and you can't match this A with this A because these are different polymorphic type variables. But this is some number of functions that go from, A to C, B to C. There's a lot going on here. That is A to B, though. So how can we take either and transform it into an A to B? This A to B, either AB. Specifically, not just either AB, but either A ent. And that's our something. All right? And this is our list. So what is this something? Well, it's not either because either has the wrong type. But if we start partially applying ethers, we can get to the right type. If we take either and feed it these two functions, so we have that, then that will have the type of that, which I think is the type we need. So, we want to take two functions and apply them to our either, or apply either to them. All right, so let's get rid of this. We want to create our map functions. Let's break this down even more. We'll do our right one first because that's easier. So our right map function is something that's going to take this right one and right two and turn it into a one or a two. So something that's going to take the structure out. No, we don't have to take the structure out because that's what the either function itself is going to do. But it needs to be a function that we could feed to either that will return the right value. Yeah, see, this is the step where I got confused. I kept thinking that I needed to destructure the left and right. But really, that's the whole point of the either function, is to do that for me. So all we need is something that, given right 5, will return 5. Or rather, something that given 5 will return 5, which is the identity function. And so that's ID. And so ID will, and this is not strictly true, right? Notionally, if you imagined that the either function only applied the right function we're making here, that's what we would end up with, right? So where right function equals ID. But now we still have this. All right, and at this point we can, let's call this X form. And let's continue to indent it that way. So we still have this hole, but I'm going to leave that hole for right now, even though it's probably obvious to you where I'm going with this. So if we know at the end of this we're going to get out our list 102, it's going to be sum step 1. So at this point I can load this, and what I expect to be able to get are types for left function. So let's take a look. Load set 3a hs. What have we got? Left function is just this type A to C, again, polymorphic. And it's not suggesting any useful holes for me. I think because the type is either, right? We still need the either to get us out of there. But in any event, told you I was wrong with that. Let's create our left map function. Actually, our either function. So in this case, we want something that no matter what value is in that left, we're going to ignore it, and we're just going to give the same value back. Which value? 0. And there's a name for that type function, which is const. So const 0 should give us back exactly what we need. Right, map x form list, either left function, right function. Our right function is ID. Our left function is const 0 with a space as appropriate. And then we sum the whole thing. It's kind of weird that I called this step 1, but that's fine. And it loads. And let's actually watch that transform. So there you go. That is how I solved sum rights with my logic kind of spun out a little more. There's another way to do this without const, I think, in that, well, they give us a challenge without pattern matching, right? We could filter out the lefts, and then we wouldn't have to bother with left function. In fact, left function could be anything probably, and it would still work. But that's just extra steps to do the same type of operation. So I don't think that's interesting. So there you go. That's how I solved exercise 11. All right, so that is exercise 3A or exercise set 3A. We will be back next week with set 3B. I hope you're enjoying this, and if you do have questions, make sure to comment in the comments and ask them there. I have seen that Professor Kassinen is on Mastodon. I hope you don't mind me telling the world about that, Professor Kassinen, and I'm sure that he would love to hear back from any of you who are watching this. Tea Leaves Programming, we're programming like it's 1979. Thanks for watching.